Hello, everybody. Welcome to the lecture of complex analysis. And in complex analysis, we are going to deal with the complex functions and its derivatives and integrals. But of course, to start with, we have to be familiar with what complex numbers are. And actually, some basic properties of complex numbers will be used very frequently when we do the derivatives and integrals. So to start with, I will conduct a very basic review of the very basic properties of complex number. So for complex number, we know that its very basic form, actually the most basic form is to write it in this complex number and x plus I, right? Where we assume that x and y are both real numbers. Okay, so this z is called complex number, and this very basic form is called the Cartesian form. Okay, so this is Cartesian form, and here x, sometimes we give the symbol of Re of z is called the real part. And the y, sometimes we give it a symbol of Inz is called the imaginary part. Okay, so this is the basic expression of complex numbers, and sometimes we actually draw a plane, like an x or y plane, and we let this x to correspond to its real part, and the y-axis corresponds to the imaginary part. And this plane, we call it the complex plane. For example, if I have x in here, if I have y in here, and then I draw this point. This is x, this is y, and I would say this point corresponds to the complex number z equals to x plus iy. Okay, this is the geometrical representation of any complex number. Okay, so in here, let's see. This is x, this is y, and this is Cartesian coordinates. That's basically why we call this form like Cartesian form. But actually, to represent the points on the plane, we can use other coordinate systems, for example, like the polar coordinates. If I say this distance, for example, I give it as r, and for this angle, I call it theta, and from a geometrical point of view, it's very easy to see that x equals to r cosine theta, and y equals to r sine theta. Right? Okay, so of course I can write the inverse relationship as, if I know x and y, then I'll just say r equals the square root of x squared plus y squared. And theta, if you just divide two equations, sine theta over cosine theta, that's tangent theta. So tangent theta equals to y over x. But here, I don't really want to write something like theta equals to arctangent y over x. That's because if you do the tangent theta equals to y over x, and if the tangent of theta is a given value, theta could still differ by 180 degrees or pi radians. So in that case, I think probably a better way is to write cosine theta equals to x over this r. R is defined here, and write sine theta equals to y over r. In this case, if you are really talking about only one cycle, like between 0 and 2 pi radians, and this theta is uniquely determined. So we can represent complex number in this way, and obviously that gives us the trig form. I would say x equals to r cosine theta, y r sine theta, plug it back in, that's z equals to, we have this common factor of r, and we put it out. That's cosine theta plus I sine theta. We can represent the complex number in this way as well. And we have to be mindful that cosine theta and sine theta are both periodic function of theta. If you add multipliers of 2 pi to the value of theta, cosine theta and sine theta will stay exactly the same. So that means for any, like for given z, this r is determined, right? R is uniquely determined. And this R equals to square root of x squared plus y squared, or I can say equals to the square root of the real part plus the imaginary part. This value, we call it, some people may call it modulus, but a more commonly used term is absolute value. Okay, I will be using this term from now on, the absolute value. And obviously the absolute value must be a non-negative real number. And for this data, we call it argument. Okay, so the symbols for absolute value, we use two vertical lines as the symbol, and we call it this equals to rho. And for this argument, we call it arg of z equals to this data. Okay. Now I have mentioned that theta, that this one, cosine theta, sine theta is periodic, right? So there are actually infinite many different choices of theta of these arguments for a given complex number. So in this way, I would say let theta naught, like in between 0 and 2 pi, like be one of the arguments of z. And if I restrict the value between 0 and 2 pi, obviously the choice of this theta naught is unique, and I call this the principal argument. And the symbol is this big R equals to this theta naught. So obviously I can say theta equals to theta naught plus 2k pi. K is an integer. Okay, but there's one special case. When this z is 0, if I just put my complex number right at origin, and there's obviously no definition for the angle theta. So R is obvious 0. Theta, I would say, undefined. We don't talk about the argument for 0. And sometimes we will also use like infinitely far away. So for complex numbers that are infinitely far away from the origin, we'd say that R is positive infinity, and we also don't talk about the argument. Okay, so this is the very basic geometrical and the Cartesian form and the trig form. Now I'm going to talk about a very important identity. Okay, I'll have to erase this part. We start with the trig form in here. This part in the bracket, cosine theta plus I sine theta, can actually be written in a more concise form of e to the power of I theta. Okay, so to prove this, we think about Taylor expansion. For real number, we know that this e to the x is actually 1 plus x squared over factor of 2 plus x3 plus x4 factor 4 plus all the way go to infinity. Okay, so when x is no longer real, when we talk about complex number, for example, if I want to raise it to the power of I theta, then we actually adopt this power expansion. But this time, it's no longer just an entity, it's more like a definition. For the definition of e to the x, we define it as the result of this operation, like 1 plus I theta plus I theta to the square over factor of 2. Then this is power 3 factor of 3 power 4 factor of 4 all the way up. Okay, now let's think about the properties of I. So I is actually the imaginary unit. We know that it's defined such as I squared equals to -1. This is the definition, right? So we know I to the power of 1 is I. I to the 2 and negative 1. So I to the 3 is I to the 2 times I to the 1. So that's negative 1 times I, so that's negative I. And I to the 4, that's literally I to the 3 times I to the 1. So negative I times I, that's negative I squared. Negative of negative 1. So we just go to unity. Go back to 1 again. Okay. So if we talk about I to the 5, then that's I to the 4 times I, so we just go back to this I, and I to the 6, that's I to the 4 times I to the power of 2. So we go back to the I to the power of 2 negative 1, and we surely know what's going on in here. We have a period of 4 and keep going on. Okay, so if we use this identity and plug it back in, let's see. E to the I theta equals to, this is 1. And I'll talk about this term first, the even terms. So I to the square is negative 1. So theta squared, that's negative of theta squared. And we have a power 2 here. This term, that's I to the 4, that's 1. So 1 is just 1. Theta to the 4 divided by 4. Then we can think that there's the 6th order term in here. I theta to the 6, so I to the 6 times theta to the 6, so I to the 6 is negative 1. And we have a negative 1 in here, that's theta to the 6, divided by 6, and plus all the way going on. Plus, now let's deal with the odd terms. This I theta is just I times theta. This I to the power of 3, that's negative I. So negative I, I'll just write this factor of I out of the whole thing. I'll write as negative theta to the 3 divided by factor of 3. So this is like negative I is I to the 3. So I to the 3 times theta to the 3, that's I theta bracket to the 3, and divided by a factor of 3. And for the 5th order term, like I to the 5 times theta to the 5. So I to the 5 is I. We already have an I on the whole bracket. So this term is just the theta to the 5 divided by 5 factorial. And then we can imagine theta to the 7 and keep going. If you are familiar with basic Taylor expansions, you instantly realize that this term is actually the Taylor expansion of cosine theta. And this term is the Taylor expansion of sine theta. So literally, we have this is just cosine theta. This bracket is just sine theta. And we just add them up, and don't forget this little factor of I. And in this case, we prove this very important identity. This identity is going to be the Euler's identity. Of course, if you plug in theta equals to pi, that is just e to the I pi equals to cosine pi plus I sine pi. And cosine pi is negative 1. Sine pi is 0. So eventually we're getting negative 1. Or e to the I pi plus 1 equals to 0. This is like the so-called the most beautiful formula in mathematics. Some people will refer to this. Okay? Right. So for this very important identity, we can just write the trig form in this way. And for this form, we're going to give it another name, which is called the polar form. Okay. So for complex numbers, we already have 3 different ways to represent them. And actually, the Cartesian form and the polar form are the most commonly used. For this form, I'm not exactly sure. We very seldom use this form. Okay, so that is just one single complex number, right? Now we're going to talk about the very basic operations between the 2 complex numbers. So think about, say, complex number 1, z1 is x1 plus I times y1. z2 equals to x2 plus I y2. Of course, here x1, y1, x2, y2, all real numbers, Cartesian form. So let's think about it. I is just the imaginary unit. when we talk about addition, subtraction, multiplication, division, it just operates as the normal like real numbers. So at least personally for me, I don't think there's anything special. Let's see. If we want to do z1 plus or minus z2, that is just x1 plus I y1 plus or minus x2 plus I of y2. I is the imaginary unit, so we just have a factor of I here, so we combine the factor without I. This is x1 plus or minus x2. And here, we combine the factor with this I, so that's I times y1 plus or minus y2. And we add them up. That's it. So from this, we can see that the real part of z1 plus or minus z2 obviously equals to, this is just the real part of z1 plus the real part of z2. And if I do a minus sign here, obviously it's the same. Okay. Multiplication and division is going to be a bit more complicated. For example, let's talk about multiplication first. Remember that I squared is just -1. So if I do z1, z2, that is going to be x1 plus iy1 times x2 plus iy2. And I'll just do it like I normally do for a plus b times c plus d. If I want to calculate this, I just expand everything out. And here is exactly the same principle. So the first term, x1, x2. This term is I times y1, x2. This term is I times x1, y2. And the last term is I y1 times I y2. Recall that I times I is -1. Right, that's the definition. So we perform this rule on the last term, and this term and this term shall be combined. So that's x1, x2 minus y1, y2. So this is the real part. As for the imaginary parts, these two terms with the I, we just combine together. That's I times x1, y2 plus y1, x2. Okay, so this is the real part. This is the imaginary part. Okay. Now, let's think about division. To do division, if we just stick with the original form like this, it might be a little bit difficult to convert it into very explicit Cartesian form. So we have to be a little bit clever in here. The trick we do is to get rid of the imaginary part of the denominator, is to actually make the bottom part real. To do this, what we do is like this. And we just multiply the same factor on the denominator as well. For the top part, we just perform exactly the same rule as how we did the multiplication. We just did it. So this time I'll directly write out the result. Okay. As for the bottom, remember that a plus b times a minus b is just a squared minus b squared. So over here, we apply exactly the same rule. That is just x2 squared minus iy2 to the square. But remember that I squared is -1. So this term actually turns out to be just the positive of y2 squared. And that's it. Okay, so this is division. So as we can see, if we stick to Cartesian form, then sum of calculation like multiplication and division is not going to be that easy. Right? So remember that we not only have Cartesian form, we can also have the polar form in here. And for division and multiplication, the polar form is actually going to bring us huge convenience. Let's see. If Z1, I don't use Cartesian form, I write it in polar form. Then if I do multiplication Z1 times Z2, that is just R1 times e to the I theta 1 times R2 times e to the I theta 2. Remember that in multiplication, we can exchange the order of terms, right? So I just reorganize all the terms. R1 and R2 goes first. Then e to the I. Remember that e to the x times e to the y is just e to the x plus y. So I can just add these numbers up. So that's I of theta 1 plus theta 2. Okay. Of course, similarly, if I do Z1 over Z2, that is just R1 e to the I theta 1 divided by R2 e to the I theta 2. And obviously, this is just R1 over R2 times e to the I theta 1 times theta 2. Okay. So, obviously, the calculation is much easier. And that is not the only point that we are using the polar form. Let's see. Remember that R is called the absolute value, right? And theta we call the argument. So from the results of multiplication and division with the polar form, we instantly conclude that this absolute value, this is the argument. This is absolute value, this is the argument. So we have Z1, Z2. This thing, the absolute value is just the product of individual absolute values. If I do Z1 over Z2, that is just the same thing. If we try to prove this with Cartesian form, that's going to give us very huge calculations. But with polar form, this is just so obvious. Furthermore, I would say, if you look at the argument, I'll write this small, argument of Z1, Z2 is just the argument of Z1 plus the argument of Z2. The argument of Z1 over Z2 is just the argument of Z1 minus the argument of Z2. Honestly, I can't imagine how to prove these two properties using Cartesian form. But again, with polar form, it's very obvious. Of course, we can extend this property a little bit. For example, this one. Like, Z1, Z2 equals to this Z1 absolute value and Z2 absolute value. If Z1 equals to Z2, for example, we call it something like Z, obviously Z to the power of 2 equals to like this. So you can literally exchange the order of power and taking the absolute value, and it's still equal. Of course, I can just extend a little bit, and if I just consider like adding more complex numbers, right? I can instantly conclude that Z1, Z2, Z3, all the way to Z, like big N. You can just stack a bunch of complex numbers in here. That equals to Z1 times Z2, Z3, all the way to Zn. The proof follows exactly the same way as in here. Of course, the argument of this whole thing is just the sum of all the individual arguments. And here, if we say Z1 equals to Z1, 2 equals to whatever equals to Zn equals to the same complex number, that is just the Z to the power of this N equals to, we exchange the order. And that's still the same, right? So, for example, if I ask you to calculate calculate this thing. If you want to calculate this term first, and then take the absolute value, that's going to give you huge trouble. But instead, we exchange the order to the power 100. And this absolute value, obviously, and that is just 5 to the power of 100. We instantly get the answer. Okay? So, it's just complex number. And lastly, we are going to talk about another operation that is unique to complex numbers, which is called complex conjugate. Okay. So, complex conjugate actually refers to, for example, z equals to x plus iy, and as always, is x and y both real numbers. So complex conjugate is defined as x minus iy. That is to say, the real part stays the same, but the imaginary part flips, changes sign. Okay. So in the language of complex plane, we take x to be the same, and y just flips. So literally, we are just taking the reflection here. If z is here, then the z star, complex conjugate. These 2 points are symmetric with regard to the x-axis, or here we may call this like the real axis. Here, of course, imaginary axis. Okay. So, let's think about a few properties of the complex conjugate. First of all, very obviously, z to the star equals to z. If you talk about absolute value, there you go. Because if you just flip the sign of y and then take the square, it's exactly the same, right? And if z equals to r e times I theta, then z star is what? Z star is actually r e to the negative I theta. Of course, here r is non-negative real number, theta is real. So this is the polar form, right? We can read this from the geometrical plot. If the theta goes this way, the negative theta goes the opposite way. We can also do the expansion like z equals to r in I theta. That is just r cosine theta plus I sine theta. So according to the definition, z star is r times cosine theta minus I sine theta. That's definition. But remember that cosine is even function, sine is odd function. So cosine theta is the same as cosine negative theta, while this sine theta is negative of sine negative theta. So this negative could become a positive, and this sine can write negative theta. So according to the polar form expansion, look at this. Euler's identity. This is obviously r times e to the I of negative theta. That's exactly the same as r to the negative I theta. Okay. So let's further think about this. Z equals to x plus iy. Z star equals to x minus iy. So what do I need to do if we want to get x from z and z star? If we add these two up, like z plus z star, that is going to give you 2x, right? So if I divide it by 2, that is just x, or I would say the real part of z. Of course, I can write z plus z star equals to to real part of z. Similarly, if I do z minus z star and divided by 2i, that is going to recover y. And that is the imaginary part of z. Or I'd say z minus z star equals to 2i times the imaginary part of z. Finally, let's look at the polar form. Think about it. If z1 is r1 e to the I theta 1, z2 is r2 times e to the I theta 2, then z1, z2, if I want to take this complex conjugate, that is just the r1, r2 e to the I theta 1 plus theta 2. This whole thing conjugate, right? And let's use this rule. If I have a polar form in here, the absolute value stays unchanged, but we need to flip the sign of the argument. So that becomes e to the negative I of theta 1 plus theta 2. Okay. So, e to the negative I of theta 1 plus theta 2, I can write it in the way of r1 times e to the I theta 1 times r2 times e to the negative I theta 2. Obviously, these two are equivalent. But when I write this form, r1 times e to the negative I theta 1, that is just the complex conjugate of r1 times e to the I theta 1, the complex conjugate, right? And this one is just r2 times e to the I theta 2 conjugate. This is z1, this is z2. So, after all these, I can just conclude that z1, z2, so the whole thing just equals to z1 to the star, z2 to the star, right? And use similar way, we can prove that the division is just z1 to the star over z2 to the star. And finally, it is actually easier to prove that addition and subtraction, this rule holds. And for this one, we don't use polar form, we use Cartesian form. I think that's very obvious. Okay, and finally, let's think about the complex number and its complex conjugate. So this z is this, z star is it. So what would happen if we take the product of z times z star? In this case, let's use this form. Re I theta times Re negative I theta. E to the I theta times e to the negative I theta. I theta plus a negative I theta is 0. So that's literally r squared times e to the 0. Well, e to the 0 is obviously 1. So that is just r squared. But remember that r is the absolute value, right? So we can conclude that z times z star is actually the absolute value squared. Sometimes using this property to calculate z squared could be even faster than directly using the Cartesian form. For example, let's calculate 3 plus 2e I theta. Theta is just a real number. Here. Let's calculate this. I will just write this as the square root of the number itself times its complex conjugate, right? This is just the conjugate. And that is going to give me 3 times 3 is 9. 2 times 2, these two factors cancel, so 9 plus 4 plus 2 times 3 is 6, 3 times 2 is 6, so it's 6 times e to the I theta plus e to the negative I theta. This gives me 13. And over here, e to the I theta is cosine theta plus I sin theta. E to the negative I theta is cosine theta minus I sin theta. So if I add them up, the sine theta factors cancel each other, but the cosine factor is going to be multiplied by a factor of 2. We have 2 cosine thetas together, so that's 6 times 2 cosine theta, and the answer is 13 plus 12 cosine theta. This is obviously faster than just expand this into Cartesian form and calculate that square root of x squared plus y squared. Okay, so these are all the basic properties I need to introduce for the basics of complex number, and now we're going to get to complex function.